What's up to you all matriculants? Welcome to your favorite show. It is a Triple M Day, Mindsetters Maths Monday with me, AB, and Tamlin. I hope you enjoyed your day at school. Let me know on Facebook if you had a great day. How was your maths class? Let me know. Tamlin, how are you?
I'm good, thanks. I had a great day at school.
Really?
For sure.
That's nice. And your weekend?
Weekend was fabulous, yes. Yeah, lots of
It
fun.
wasn't that short, hey?
The weekend? No, yeah, it always is a little bit too short, actually.
That's what I was waiting for. But otherwise, what are we doing today?
Today we are extending what we did last week with a bit of calculus, and this week we're having a look at cubic graphs.
Yeah, I
So-
must say, it shouldn't be something that is strange to the mindsetters, because from last week, John giving them the basics, most of them gave us that reaction that we are not commercial students, we are not physics students, we're
Yes.
just commercial students. But I should say, it was just basics, and
Absolutely.
whatever that we've done last week, it's going to help you this week. So make sure that you also get last week's notes, because they're going to help you.
Absolutely. Go and practice your test yourself questions on our mindset notes, because a lot of what was learned last week is actually being reinforced there as well. So you cannot do enough reinforcement of all of that work. So definitely go and do that.
Awesome. And you know, with us mindsetters, you're always a step ahead. So go to facebook.com/learnextra, like the page, share the page, and speak to me, chat with me on Facebook, and let me know how was your day. Are you struggling anyway? If you have questions, feel free to throw them to all of the mindsetters, because we are a team and a family that wants to help one another. On Twitter, follow us at learnextra. And now we're giving you also the notes for free, guys. We have two options for you. It's the view and the download, and also test yourself question, all on Facebook. The links are on Facebook. On the test yourself questions, you've got questions that will put you on a chance to stand a chance of winning this awesome Casio calculator. By answering all the correct questions, you stand a chance of winning this awesome calculator. I'll be announcing the winners later on. One last thing, we have MoMaths app, which is a mathematical application, which when you go to MoMaths, momaths.org, you stand a chance of competing with all other mindsetters across the country. Test yourself and see if you understand what we're doing today. Your code is I2IK. I2IK. So make sure that you have that code. I'll also post it on Facebook. Tamlin, over to you.
Fantastic. Right, grade 12s. As we said, we're going to be having a look at cubic functions today. What you learned last week, where we learned how to find the derivative by means of first principles, and then you learned finding your derivative using your rules of differentiation. So those have all laid the groundwork for the next part of this today, which is our cubic functions. So let's have a look at our summary and just a description of what it is that we're going to be doing today. Right, first things first, what we're going to be having look at is how to sketch the cubic functions, okay? The standard form of our cubic function graph is in the form of ax cubed plus bx squared plus cx plus d, okay? So that's your standard equation. When we've been given our equation and we actually have to sketch the graph, that's what we're going to be having a look at first. Once we know how to sketch the graph, turning it around, the other way of looking at it is if we actually are given the graph and we have to determine the equation, all right? We should be fairly used to that by means of having done functions in grade 11 with parabolas and all different types of functions. This is just adding to it. So we're adding another type of function that we find the equation of. And then we're also going to have a look at, which is quite an interesting concept and a new concept to us in calculus, is that if I'm actually got the graph of the derivative, okay, and we work with the function of the derivative and actually interpret it and are able to work out certain things about your cubic graph from having the derivative function. So those are the things that we're going to be having a look at today. Let's see if we can have a quick look at our challenge question. All right, so during the course of this lesson, we're going to be discussing how we sketch the graph, how we find the equation of your graph, and also all sorts of different interpretation questions of your function. So quickly just having a look at it, your challenge question for today is that what we've been given is the graph of f. All right, it's been defined by your standard equation of y equals ax cubed plus bx squared plus cx plus d, all right, as well as a straight line graph. So we've got our cubic function and we've got our straight line graph, which has been defined by the equation y equals 7x plus 14, all right? The other piece of information that has been given to us is that we have a turning point. Point B over here is the turning point of our cubic function, and that's the point of 2 and 0. And that's it. That's the information that's been given to us. So the questions that are needing to be asked or answered with regards to this diagram are the following. The first thing we want to know is what are find the values of the coordinates, of the points A, B, and C. So what I'm referring to is these over here, the A, the B, the C, and the D of your cubic function, okay? I want to know what those are going to be. Once we've done that, we need to determine the length from D to E, so we want to know the length from D to E. We need the coordinates of A being a turning point, so we want to know what the coordinates of the turning point are. The point of inflection is the point where your graph goes from being concave down to changing to be concave up. So the point of inflection, which we will discuss shortly, so we'll determine how we do that. And finally, to determine the equation of the tangent to the curve of f at E. Okay, guys, so that's your challenge question. It is quite a challenge, quite a lot of work to do with that. So let's work through it carefully, and let's see how far we manage to get with that. I'm sure you guys will find it quite easy once we've actually gone through all the theory and practiced a little bit with it. Looking at our summary. All right, so as I've already had a look at, and as I've already said, your cubic graph has a general equation of the following. All right, ax cubed plus bx squared plus cx plus d. So if the equation has been given to us and we have to sketch the graph, you're going to recognize it as a cubic function because of the fact that you've got your ax cubed plus bx squared plus c. And there may be elements of that that are missing. You might not have every single piece of the equation there, but it does need to be an x cubed. Okay, that is going to tell us that we've got our cubic function. All right, generally speaking, just in terms of the shape of your cubic function, if your a value, the a value being this one over here, if your a is greater than 0, so in other words, if the a value of your equation is positive, all right, that implies that we have a positive shaped function, all right? The shape of a positive cubic graph will begin by increasing, okay? So from negative, as we're going from left to right on your x-axis, it will begin by increasing. At your first turning point, it will then decrease, and at your second turning point, it will then continue to increase, okay? So that is your positive cubic function, and that's determined by the value of the a being positive. However, if the a value is less than 0, so if I have a negative a value in the equation, the shape of your cubic graph is going to look like follows, okay? As we're reading from left to right on your x-axis, your graph will begin by decreasing up to the first turning point. It will then continue to increase, and at the second turning point, it will then decrease. Okay, so the a value determines, just like it did with a parabola and a hyperbola and all your different functions, the a determines the positive or the negative nature of your function. Okay. Rules for sketching a cubic graph. Okay, so once again, I can relate this back to sketching graphs of a parabola, for instance. Let's think back on that for a second. If you had to sketch a parabola, the information that you needed, that was necessary, was things like, was it a positive parabola or was it a negative, which was determined by your a value? What were your x-intercepts? And remember, with any function, to work out your x-intercepts, we let y equal 0. Y-intercept, we let x equal 0. We needed turning points. Okay, so these are all pieces of information that are necessary in order to actually put that sketch together. All right, so to sketch my cubic function, we need the y-intercept, and just like any other function, we do that by letting x equal 0. The x-intercept, and we work that out by saying let y equal 0. Now there's something interesting regarding your x-intercept. Because it's an ax cubed function, okay? The degree of that equation is x cubed, which means that you're going to land up with 3 answers for x when we actually let y equal naught there, all right? So with any of your equations, if I look at a quadratic equation, I had ax squared. Because it was ax squared, you knew that you were only going to land up with 2 answers for x, for your x-intercepts. Ax cubed, 3 answers for x. All right. Stationary points. Okay, so what we've learned is that a derivative, we learned this from last week, a derivative is the gradient of a tangent, or it's another way of rephrasing that, it's the rate of change at one point, okay? Now, if I were to think about this, if I were to draw a cubic graph quickly, like that, and let's draw ourselves a tangent to that graph at the turning points. Okay, so that's going to actually, let's move that up slightly. Can we do that? No. All right, sorry, let's just go back a sec. Let's take that away, and I'm going to just draw my own line there. We're going to draw ourselves a tangent as straight as we can at the turning point over there. All right? If ever we draw ourselves a tangent to the cubic graph at the turning points, what we should notice is that that line has no gradient, okay? There's no slope or there's no slant to that line. So therefore, there is no rate of change. And if something's got no rate of change, it's stationary, all right? There's no change in it. So therefore, when we talk about the turning points of our cubic function, we refer to it as the stationary points. Why? Because if I draw a tangent to the function at those points, there is no rate of change. Now let's think about that. The derivative, so therefore what we know is that the gradient of your tangent would be, there wouldn't be a gradient. So therefore the maths behind that would be that what we would have to do is calculate the derivative of your function or the equation, and we always let it equal 0. All right, so that's really important, guys. When you are wanting to work out the turning point or the stationary point of your cubic graph, we always let the derivative equal 0. Okay, and that will always give you the stationary points of your cubic function. Right, once you've actually let the derivative equal naught, okay, what you've obviously landed up with is a value for x, all right? You'll typically have 2 values for x. What we would need to do with it is work out the values for y. So we sub it into the equation and we get a coordinates for x and y of your stationary points. Okay, the 2 stationary points, just to quickly clarify, we're going to get one that's a maximum and one that's a minimum turning point, all right? And that would obviously just quickly look something like, for instance, this being your local maximum and your local minimum, okay, at those 2 stationary points. Right, your point of inflection is the point where your graph changes from being concave up to concave down, okay? And the way we calculate our point of inflection is we work out the second derivative. We find the second derivative of your f of x equation, and you let that equal 0. Once again, giving you a value for x, which you must remember then to substitute back into the original equation, because that will give you the coordinates, the x and the y coordinates of your point of inflection. All right. And that once you've got all of that information, and that's quite a lot of working out. So you'll see in your exams, to sketch a graph actually comes up, it adds up to quite a lot of marks in the end, because there's quite a lot of working out that needs to be done. So once all of that's in place, you can then sketch your graph, making sure that everything is very clearly labeled and very clearly marked. Okay. Looking at it from the other perspective, if I change it around, say the graph is actually given to us and we have to determine the equation, all right? What do we need to know? What kind of theory do we have to fall back on if we actually have to find the equation of a given graph, okay? Well, the first thing I would say you need to look at is you need to ask yourself, what information do you have? And the first thing is, do you possibly have the x-intercepts of the graph already, okay? Because if you do, then the first formula that's going to come to you is this one over here, where I've got y is equal to a, x minus x1 multiplied by x minus x2 multiplied by x minus x3. And this x1, x2, and x3 will be substituted with the 3 x-intercepts that you already have, all right? Once you've actually substituted those x-intercepts in, you need to find the value of that a, all right? That needs to be solved for as well. And typically, you will be given another point on that graph somewhere. which we substitute into the y. We substitute into the y as well as the remaining x values. And by doing that process, you're going to work it all out, and you'll be able to find the equation of your cubic graph, which is in the form of ax cubed plus bx squared plus dx plus d. Okay. Finally, before we go for a quick break, sorry, I'm jumping around now. Oh, goodness, sorry. Why is it jumping? Let's just go down to the bottom. All right. Right, there we go. All right, and okay, so last thing is just quickly this over here. This is interesting over here, grade 12s. If you have been given a graph and you have to find the equation of the graph, and this is what it looks like. All right, this is a brief sketch. I've got one x-intercept over here, and I've got another x-intercept over there. So what I've just explained to you is that in order to use the previous formula, you needed to have 3 separate x-intercepts in order for this to work, all right? So what would happen if I actually had a cubic function? I can see it's a cubic function, but I've only got 2 x-intercepts, all right? What you would then look at is that this x-intercept over here is not only just an x-intercept, but it actually functions as a turning point as well, all right? And if that's the case, the formula that we need to work with is we have our x minus x1 multiplied by x minus x2, but the point that doubles up as an x-intercept and a turning point gets squared, okay? And that will then process out, and we'll FOIL it and do everything that we need to do to actually come down to the formula at the end. So watch out for that. If the point actually sort of doubles up as an x-intercept and a turning point, in the equation to find, in the working out to find the equation, we square that bracket. Okay. Right, last thing before we go for a break. If you haven't been given x-intercepts, but you've been given turning points, you automatically go to your derivative equals naught. So you would work out the derivative of the equation, equal it to naught, and you would substitute turning points in. So we're going to have a quick break, and then I think we're going to get into some examples to actually prove all of that theory to you.
I'm sure we really need that, and you guys also need that break. But a big shout out to Spiro, who's watching, Formation Marsha on Twitter, also who's watching, enjoying the show. Please send through your questions if you're struggling anywhere. Mindsetters, we're here for you. See you after the break. Welcome back, Matrix. Now, one thing that I love about Learn Extra Live is that it accommodates everyone. It is a family show. There are people who are watching the show with their grandparents, their mothers, their fathers, which is so cool, guys. A shout out to Priska, who's saying, hi, everyone, AB. Please send a shout out to my grandmother, Aus Onika. Hello, who's watching with me. Love a lot and love mindset a lot. Thank you so much. That's from Priska Lomsiki. So thank you so much. But before I get carried away, let me tell you guys that remember, you must go to More Maths, which is a cool mathematics app to challenge yourself and also to challenge other mindsters. Your code is I2IK. So simple, guys. And if you're struggling, we're here for you. The challenge question is on Facebook. There's just so much for you guys to do, and we are here to help you.
Right, let's get going, guys. We've spoken about how we go about sketching a cubic graph and how we go about finding the equation of a cubic graph. But let's put a little bit of some of that theory into practice, okay? The first example we're going to have a look at over here is that we have been given an equation which is in the form of f of x equals negative 2x cubed plus 5x squared plus 4x minus 3. And we are required to draw a sketch of f of x. And they've just specified that we need to clearly indicate x-intercepts, y-intercepts, turning points, etc. Okay. So let's break this down into steps. The first thing that we need to establish is what kind of shape is this cubic function going to have? Is it positive or is it negative? Now, by looking at my equation, this negative 2 over here is the value of your a. And remember, we spoke about it previously. If your a is less than naught, it is negative. So I know that my shape of my cubic function is going to start by decreasing. It will increase between the two stationary points, and it will continue decreasing infinitely at the end. Okay, so that's step number 1. Step number 2, let's quickly establish our y-intercept. Y-intercept is always quite nice and easy because all we have to do is let x equal 0. And if I let x equal 0, I would have negative 2 times by naught cubed. I would have 5 times by naught squared. 4 times by naught minus 3, which means that everything cancels out, and we are left with y equaling negative 3. So that's our y-intercept, done. Now we need to work out our x-intercepts. Okay, the x-intercept is generally the one that requires a little bit more working out. Okay, so let's work out our x-intercept. And this is where we say let y equal naught. Okay, so I've got naught is equal to, let's just get back to our equation. It was negative 2x cubed plus 5x squared plus 4x minus 3. Okay. We are going to have to use a method that we learned in previous lessons called your factor theorem here, okay, because we need to factorize this cubic expression. So, first things first, because it is equal to naught, this negative, we can take out negative, we can basically divide everything through by negative 1. And as a result, naught divided by negative 1 is still just naught. I'm going to have positive 2x cubed, negative 5x squared, minus 4x plus 3. So everything has been divided through by negative 1. Now, using the factor theorem, we need to establish a factor. We need to find, and it does mean by means of trial and error, find a factor that will give us an answer of 0 when I substitute values into x, okay? Now, when we say it's trial and error, it's guided trial and error, because what we need to do is look at the last term. I need to look at this 3 over here. Whatever I substitute into x has got to be a factor of that 3, which limits me down quite severely down to really just 1 and 3, or if those don't work, we have to try negative 1 and negative 3. All right. So let's start and let's do a bit and see what we can do. I'm going to substitute x equals negative 3. Okay? So I've chosen that as a value. Let's see if we'll end up getting naught. So what I'm working with is f of negative 3. So we have got negative 2 times by negative 3 cubed plus 5 times by negative 3 squared plus 4 times by negative 3 minus 3. And what we need to do is we need to put that in our calculator, and let's see if that gives us 0 when we work it all out. So I've got negative 2, negative 3 cubed, plus 5 times by negative 3 squared, plus 4 times by negative 3 minus 3. And okay, no, so that didn't work. Let's try positive 3. Let's see if positive 3 works. So negative 2 times by positive 3 cubed, plus 5 times by positive 3 squared, plus 4 times by 3, am I right? And then minus 3. Yes, okay, it gave us 0. So the negative 3 didn't work, so I tried positive 3. That got me what I was looking for. So what I know, therefore, is that x, if positive 3 was the number I substituted into x, if I put it back into the brackets, x minus 3 is a factor. Okay? Now that I've established that x minus 3 is a factor, we need to work out how many times does x minus 3 go into our cubic equation. Now, there were methods that we learned how to do this, one of which is synthetic division, okay? This is just one of the methods, grade 12. You may have learned a different method, and really, whichever method works that you understand and that works for you, we're happy for you to use. I'm going to use the method of synthetic division, and that looks something like this. We take a divide and we take all the coefficients of your term. So I take negative 2 plus 5 plus 4 minus 3. So just to show you where they came from, I'm taking just the coefficients of each term. All right? And x minus 3 was your factor, so we put positive 3 outside that bracket over there. Okay, the method is that we bring negative 2 down, and we multiply. 3 times by negative 2 is negative 6. Positive 5 minus 6 is minus 1. And I multiply again. 3 times by negative 1 is negative 3. 4 minus 3 is 1. And multiply again. 3 times 1 is 3, and what you always want here is you want an answer of 0. If you get 0, you know that you've done it correctly, okay? And filling in our descending powers of x, we've got negative 2x squared minus 1x plus 1. Bear in mind that we did have this equal to naught. So because it was equal to naught, I can get rid of that negative. So it's plus x minus 1. So that's how many times x minus 3 factorized into the cubic equation. And I need to factorize it one more time. So this trinomial we're going to factorize. So we're going to have 2x and x. Factors of 1 will be 1 and 1. And we're looking for a negative, so I'm going to have minus 2x and plus 1 will be the factorized answer over there. This all being equal to naught, because don't forget that was what we're trying to do to work out the x-intercepts. So after all of that working out, the 3 x-intercepts are negative 1/2, 1, and 3. Okay, so I've got my shape, I've got my y-intercept, I've got my 3 x-intercepts. What I now need to establish are my turning points or my stationary points, okay? And in order to do that, we let our derivative equal 0, all right? The formula was, sorry, let's just go back to it. It was negative 2x cubed plus 5x squared. So let's just write that down. Negative 2x cubed minus 5x squared. And let's just get the other part of it. Plus 5x squared plus 4x minus 3. So that was plus 4x minus 3. Okay? Now what we know is stationary points require us to find the derivative. So therefore our derivative is going to be negative 6x squared plus 10x plus 4. And the derivative has to be made equal to 0. All right? So this leaves us with a trinomial to work out, or a quadratic equation. Let's divide everything through by negative 2. That's going to leave us with 3x minus 5x minus 2 equals 0. And because it's equal to 0, I can divide by negative 2, and that will cancel. All right. Okay, and it's a trinomial, so let's factorize. I've got 3x, and I have got x. Factors of 2 is 2 and 1. We're going to have to put our 2 and our 1 in those positions there because we want a negative 6 and a positive 1. Leaving me with two values for x of negative 1/3 and positive 2. All right. So what have we found? We have found the x coordinate of your stationary points. But like any point, if it's got an x coordinate, it needs a y coordinate. So we are now going to have to substitute. We're going to have to work out f of a negative 1/3, and we're going to have to work out f of 2. Okay? And let's quickly see if we can do that. Right, so we have got, let's see if we can go back. Let's clear that. All right, so we have got negative 2. Now what I'm doing is I'm substituting this back into the original equation, always back into the original equation, and we are cubing that, plus 5 times by negative 1/3, negative 1/3 squared, plus 4 times by 1/3, negative 1/3, sorry, that's, otherwise you're going to end up having problems there, negative 1/3, and then close that bracket, and finally minus 3. Right, so what is that giving us? Okay, that looks like a very difficult point to plot, but if I change it to a decimal, negative 3.7 looks a bit more realistic. So negative 3.7 is the point over there that we're going to have as a y coordinate, and if I substitute 2, I've got negative 2 times by 2 cubed, plus 5 times by 2 squared. No, that's, oh goodness. Let's try again. Negative 2 times by 2 cubed, plus 5 times by 2 squared, plus 4 times by 2 minus 3, and we're getting 9. Right, so they're my turning points. So I have negative 1/3 and negative 3.7. I've got 2 and I have got 9. So let's sketch this graph over here. So we're going to give ourselves x and y axes. And let's see, we knew that we had, let's go back to the x and y intercepts. Let's go back up here for a second. Right, x-intercepts were at the y-intercept. Y-intercept was at -3. My x-intercepts were at, let's go down a little bit further. X-intercepts were at -0.5, 1, and 3. So -0.5, 1, and 3. All right, so we had -0.5, 1, and 3. Turning points. Turning point was at -1/3. Okay, -1/3 and -3.7. Okay, I'm just estimating. I'm not having, it's not to scale. 2 and 9. So if that's 2 and 9, we've got our points up here. And just one final thing to remember was at -3. Yes, okay, so the y-intercept was at -3. All right, so it's a decreasing function, so it begins by decreasing. It passes through my first x-intercept. It gets to my turning point where it turns around. It comes up through your y-intercept, all the way up. Okay, that's missed that point slightly. Sorry, my sketch is not 100% accurate. And it turns around. Let's just fix this point over here to make it look a little bit nicer. Go back to here. Let's just sketch that a little bit better. So that will go through there, and this point over here was 1. It was 1. Okay. All right, so we therefore have our f of x function, and just label, give the coordinates of your turning points, and just make sure that everything is clearly labeled. All right. Okay, guys, so a lot of working out, as I mentioned before, but obviously it's all worth valuable marks. If we had an equation such as this, okay, can you see that I've got x cubed minus 3x minus 2? It is missing your x squared term, all right? There isn't an x squared in there. However, I know it's a cubic equation because it's got an x cubed in it. So we would follow all the same steps. They would go through the same process. Shape, y-intercept, x-intercept, using your factor theorem, stationary points, point of inflection, which is, remember, your second derivative equals 0. And that will then give me all the necessary information to sketch your graph. Okay, right. Let's have a quick look at something that's given to us in this form, because this is another way that we could find information and be expected to sketch a graph given information in this format over here. They've told us to sketch the graph of a cubic function that's continuous for all values for x and has the following properties. Now, at first glance, this looks completely different to what we were doing previously. This doesn't look anything like what we know. But if we just take it and carefully break it down, we should find that, in fact, actually this all is information that we do know. If I've got f of -3, well, -3 is now being substituted for x. So essentially what I've got there is a value for x, where x is -3, y is 4. Okay, so how can I interpret that information? I've got a coordinate point. I've got -3, and I have got 4 as a coordinate point. All right? Let's see the next piece of information. The f prime of x, so in other words, your derivative is at -3 is equal to 0. Okay? Well, what do we know about the derivative equal to 0? We know that that's its stationary point. So what can we interpret from here is that we have got a stationary point at x equals -3. Okay? All right? I'm going to save these two pieces of information for last. Let's just deal with this over here. F of 1 equals 32. So similar to the above example, if I've got an x coordinate of 1, I've got a y coordinate of 32. And if I've got f prime of 1 equals 0, well, that again means that where your derivative equals 0, it's your stationary point. So we know that we've got a stationary point at x equals 1. Okay, so we've now got to take all this information and we've got to sketch a graph from it. So let's see what we can do here. Let's draw ourselves our x and y axes. And let's plot what we can. Let's just see what we've got to start off with. I know that I had a point of -3, so that's -3 and 4. So let's give ourselves a little point over there. I've got 1 and 32. Now again, obviously these graphs are not always to scale, so we're going to have to give ourselves a little bit of leeway there. But so for what it's worth, we're going to mark that off as 32. Okay, it obviously should look a bit higher, but my space is limited here. Okay, let's just neaten that up. Okay, so there's that point over there. So I've got 2 points over here and over here. What I know is that at x equals -3, I've got a turning point. Okay, so what I know is that I've got a turning point over here, and I've got a turning point over here. Okay, well that's interesting because now I know that the shape of, I don't know at this point, in fact, what the shape of my graph is. I don't know if it's positive or negative. So that's a bit tricky. And I know that it's got to turn somewhere along this dotted line over here, and it's got to turn somewhere along that dotted line over there. So this is where this piece of information becomes handy. Where your second derivative at -3 is greater than 0. This implies something called your second derivative test, okay? And very briefly, your second derivative test says this. Where your second derivative is less than 0, so once you've worked out your second derivative and you've substituted your x value into it, and you've landed up with a value greater than 0, that is the point at which it's its local minimum. And your second derivative, once you've calculated it and you've substituted your value for x into it, that implies, and if it's less than 0, so in other words, where this is negative, it actually gives you your maximum. So therefore, I know that this point over here is going to be your minimum, and this over here, your maximum, and I know that from my second derivative test. So I know that it's going to be my minimum, so therefore my graph is going to look something like this. It's going to decrease up to my turning point over there. It's then going to turn around and it's going to increase up to where my second turning point is, and then it will decrease again. And that was the rough sketch of that cubic graph based on the information that they gave me, which looked quite strange initially, but if we just took a moment to actually break it down and carefully analyze what they've been telling us, all that information is actually quite common and quite well known to us. So there we go. So that's a very interesting question, and one which can very possibly come up for you guys. So go and practice a couple of those. Are we due for a break?
Yes, we are.
Okay.
Thank you. Sorry, Mindsetters. Thank you so much, Chamberlain. And Mindsetters, now the moment that we've all been waiting for to hear the winner of our Test Yourself question from last week's show. Our winner is Andrea Sitole. Andrea Sitole, congratulations. You have won yourself this awesome Casio calculator. After the break, we'll be tackling the challenge question. See you. Welcome back, Matrix. Now, there's a tweet from Formation, Masha, that says, just maths, trigonometry. I would like to say good luck to my classmates at Nkotwane Secondary School. Please, man, tell them. I just told them all the best, guys, when you're writing your exams. I know that some of the Mindsetters are writing, so all the best. You've been saying this on the page. Good luck, guys. Practice makes a perfect, and the only time you can know it is by practicing and ask when you do not understand. But now I think we're going to do the challenge question.
Let's have a look at the challenge question. Okay, so this is what we had. We had an equation that was defined by y equals negative x cubed plus ax squared plus bx plus c. Okay, so that's what has been given to us as far as the cubic equation goes. The straight line graph is the equation y equals 7x plus 14. Question 1 has asked us to determine the value of the a, the b, and the c. That was question 1 over here. Find the value of a, b, and c. Okay, and the a, b, c relate to the variables in your equations of your a, your b, and your c. Please note that the first term, the coefficient of your x cubed, is already known. We already know that that's -1. Okay, so just take note of that in a test. If you're actually only needing to find 3 of the variables, one of them is actually possibly already known, which in this case it is. Okay, right. So we are having to find the equation of my function. So therefore, as I mentioned before, we need to consider what information has been given to us. And if we look carefully at the graph, I've got an x-intercept of -3, and I've got another x-intercept at 2, but that x-intercept happens to also be a turning point. So if you recall, the equation that we need to start off with as an introduction is x minus x1 multiplied by x minus x2, but because of this point of being both a turning point and an x-intercept, we square it. Okay, so that's important. That's the starting point. Now I need to substitute in this. Now this a over here, in this case, represents the value in front of your x cubed. All right, the value in front of your x cubed, which is that term over there. And in this case, it's already known. I know that it's negative 1, so that's getting substituted in there. X minus negative 3, that's the first x-intercept, which becomes positive 3. And x minus 2 squared is the next term, okay? So now what we need to do is multiply this out. So I've got negative 1, I've got x plus 3, and I'm going to square out my second bracket, leaving me with x squared minus 4x plus 4, okay? Let's now distribute, let's FOIL this out. So I've got negative 1. This is going to have to now multiply to all 3 terms. So I'm going to land up with x cubed. I'm going to get negative 4x squared. I'm getting positive 4x. I then take negative 3, a positive 3 at least, and I do the same thing. I multiply it to all 3 terms. So I get positive 3x squared. I get negative 12x. And I finally get positive 12 inside your bracket. So now it's needing to have a whole lot of tidying up happen over here. X cubed is going to stay x cubed. Negative 4x squared plus 3x squared is going to leave me with negative 1x squared. Positive 4x minus 12x, I'm going to land up with negative 8x. And finally a positive 12. And I'm going to distribute the negative. So therefore I get negative x cubed positive x squared plus 8x minus 12. Okay, so the question was asking what was the value of the a, the b, and the c of the given equation. The a was what was in front of your x squared. The b was what was in front of your x, and the c was what was the constant term at the end. So to answer my question, the a is a value of, the value in front of your x over there is just positive 1. The b, all right, b is the value of 8, and c is the value of negative 12. All right, so there we go. That's the first part of the question done. Now they're asking us to find the length from D to E. So we identified it at the beginning of the question. Point D is right there, and point D is right there, and we need to find the distance from D to E. Well, what we should identify for each one of these points, this one and that one, is that they are the y-intercept of both of your graphs. Okay, the y-intercept of a straight line graph is that value over there. So we know that this is 14. And the y-intercept that we've just worked out on your cubic graph is negative 12, which is down here. So therefore, how many units, how many jumps is it from point D to point E? Well, it's going to be a total of 26 units. So DE, so my distance from D to E is going to be equal to 26 units. Okay. Right, then the coordinates of A. The coordinates of A, well, that's a turning point. It's a stationary point, all right? We already know that the stationary point, the maximum stationary point is at 2 and 0. We need to work out what the minimum one is. So we need to, stationary points always require us to work out the derivative and let it equal 0. So let's work out the derivative. We are going to have negative 3x squared plus 2x plus 8, and remember the 12 falls away because there's no x there, and it's equal to 0. Let's divide through by negative. Let's get rid of that. So I'm going to have negative 2x minus 8 equals 0, and let's factorize this quadratic equation. Okay, so factors of 3, we're going to have a 3x and an x. Factors of 8, let's see what we've got here. 4 times 2, 6 and 4. If I put my 4 there and my 2 there, if I make that a negative 6 and a positive 4, we'll land up with negative 2. Okay, so my first turning point will then be at negative 4 over 3. And my second turning point is at 2. Now what's quite nice over here, grade 12s, is you can verify that answer. That turning point of 2, we already knew that. If I go back to my picture, that turning point of 2 is already there, okay? So the negative 4 over 3 is going to have to belong to point A, which is a negative x value. I can see on the graph that it's a negative x value. So the next step here is that if I know that the x coordinate is negative 4 over 3, I'm going to have to substitute that back into the original graph to work out the y coordinate, okay? So subbing it back into the original function is going to give us the y coordinate. Let's quickly do that. Our original function was negative x cubed plus x squared plus 8x plus x squared plus 8x minus 12. And obviously now what we need to do is take out our calculators, and everywhere, oh dear, now I've just lost it. Okay, I'm going to get you guys to do that, otherwise I'm going to fiddle around with this. Take your negative 4 over 3, substitute it into your values for x, and obviously what you'll land up with is the y coordinate at your turning point. Okay, so that's the method that we need to follow over there. Oopsie, we don't want that. And let's see the next question. Any points of inflection, all right? Your point of inflection is your second derivative equals 0, all right? So your point of inflection, we now need to take your derivative, which is your negative 3x squared plus 2x plus 8. We let the second derivative equal 0. So the second derivative is going to be 6x, let's just check, negative 6x plus 2, and we're letting that equal 0, and we solve for x. So negative 6x equals negative 2. X is equal to negative 2 over negative 6, which can simplify to 1/3. Again, you've got the x coordinate there. You still need the y coordinate because they're asking for a point, and a point involves an x and a y coordinate. So you would now need to take your x value, and you must substitute it back into the original equation. Please don't substitute it back into the derivative or the second derivative. We always substitute the value. If we've got an x value and we're looking for the y value, you sub it back into the original equation. All right, and finally, the equation of the tangent to the curve of f at E. So we're looking for the tangent. So at E, if I were to draw a tangent to my curve at E, where it's touching E, okay? That's not going to, actually, no, that doesn't sketch so nicely because it's only supposed to touch at one point, okay? But what do we know about calculus? To find the gradient of a tangent, we need the derivative, okay? So if our equation, let's see if we can do it underneath here. I'm going to do it in green so that we don't get confused. I'm going to take it to find the equation of a tangent. That's in the form of y equals mx plus c. We know that. The gradient of your tangent is found by means of the derivative. All right, so if I work out the derivative of this function over here, we had negative 3x squared. I have plus 2x plus 8. And they said it was at the point E, all right? And at point E, we had the coordinates of what? That was the y-intercept of your graph. And the y-intercept has the coordinates of x being 0 and y being negative 12, all right? So therefore, the x value of 0 is going to get substituted into that derivative because that's the point at which it touches. So that squared times by 0, 2 times 0 plus 8, leaves me with 8, which means that the gradient, this value over here, the m, is going to be 8. All right? So we have y equals 8x plus c. And then we need to take the actual point of E. E being the coordinates of 0 and negative 12. And to work out your y-intercept, your c, we're going to substitute negative 12 into the y value, 0 into my x value, and that's going to give you c, which is negative 12. So the equation of your tangent to the graph at E is y equals 8x minus 12. All right. Okay, so there was a lot of working out with that challenge question, guys, but typical to a question involving cubic graphs. So just make sure that you are very comfortable with using your factor theorem and finding factors, that you're comfortable with finding the derivative and letting it equal 0 to work out your stationary points. Another concept, please make sure you practice, is finding the equation of your graph based on information that's been given to you. So as our example was over here, we had x-intercepts, so we knew to substitute it into our x minus x1 multiplied by x minus x2 graph. Okay. Abram, I know that there was a learner who asked a question, so seeing as you've got a little bit of time, let me quickly answer one question a learner had. The question was, let's go back to here, I think it was this question here. Can a cubic function only get one x-intercept? Now, the answer to that is yes, it could, all right? If I had a function such as this y equals x cubed plus 8, if I were to factorize that, okay, don't have time to do it all now, but I'm going to tell you that the only factor of that graph over there, or the only value for x that's going to work, is x equals -2. Okay, that's it. There are no other values for x. So how do you sketch that graph, okay? If I've got a cubic, if I've got my x and y axis, and the only x-intercept I know I've got is -2. I know, because this a is positive, I know that it's increasing. So it's going to increase up to the point of your x-intercept. Now that lands up being 8 over there, which happens to be your point of inflection as well. You would work that out with your second derivative equals 0. So what would happen is that it turns around and it continues to increase. So that's what it would look like, okay, if you only had one x-intercept. And that does happen, so just look out for those. Okay, guys, I think that's all the time we have for today, but I hope you learned a lot about cubic graphs, and go and practice now. It's all about the practice.
Exactly. Thank you so much, Chamlin, and thank you, Mindsters, for tuning in. Really appreciate it, and I hope you have learned so much. Remember, guys, for the more maths, you need to go to moremaths.org, and your code is I2IK. That's how simple you can now practice your maths 24/7, and you have it at your fingertips. We love you guys, and keep on believing in yourselves, because when you stop believing in yourself, no one will ever believe in you. And from me, AB, and the rest of the team, peace.